For much of the 19th century, classical physics was seen as a nearly perfect description of nature. The laws of motion, thermodynamics, and electromagnetism seemed capable of explaining everything from the movement of planets to the behavior of electricity and heat. This confidence shaped how scientists thought about the universe. Nature, they believed, operated smoothly and continuously, like a well-oiled machine. Energy could change form, but it flowed without interruption. Within this intellectual climate, the problem of blackbody radiation slowly emerged as a quiet but deeply troubling contradiction. A blackbody is an idealized object that absorbs all incoming radiation and re-emits energy solely based on its temperature. While such an object does not exist perfectly in nature, many real systems come very close, such as heated cavities, stars, and glowing metal. When physicists studied how these objects emit light and heat, they found a clear and repeatable pattern. As temperature increased, the object emitted more radiation, and the distribution of that radiation across different frequencies followed a precise curve. Experiments produced remarkably consistent results, yet theory stubbornly refused to agree. At first glance, the problem seemed manageable. Classical thermodynamics could explain how total energy increased with temperature, and electromagnetism described light as a wave propagating through space. Combining these ideas, physicists attempted to calculate how energy should be distributed among different frequencies inside a heated cavity. The reasoning was logical and elegant. A cavity could support electromagnetic waves of various wavelengths, much like a musical instrument supports different notes. Each wave mode should carry energy, and at thermal equilibrium, energy should be evenly distributed among all possible modes. This idea, known as the equipartition theorem, worked well in many areas of physics. It successfully explained the behavior of gases and many thermal systems. There was no obvious reason to doubt it, but when applied to blackbody radiation, the results were disastrous. The calculations predicted that as frequency increased, the energy emitted by the blackbody should increase without limit. According to classical theory, a hot object should release infinite energy at very high frequencies, especially in the ultraviolet region. This prediction was not just slightly wrong, it was catastrophically wrong. Experiments showed the exact opposite behavior. At low frequencies, radiation increased as expected, but beyond a certain point, it peaked and then dropped sharply. High-frequency radiation was limited, not infinite. The mismatch between theory and observation was so severe that it became known as the ultraviolet catastrophe. The name reflected both the mathematical divergence and the sense of crisis it created among physicists. What made this failure particularly unsettling was that each part of the classical reasoning seemed sound. Maxwell's equations describing electromagnetic waves had been verified countless times. Thermodynamics was considered one of the most reliable frameworks in all of science. The equipartition theorem had an impressive track record. Yet when these trusted ideas were combined, they produced nonsense. The implication was unavoidable. At least one deeply held assumption about nature had to be wrong. Physicists tried to fix the problem without abandoning classical principles. Various models were proposed, each attempting to modify the distribution of energy in subtle ways. Some adjusted how waves interacted with matter, while others introduced mechanical analogies involving oscillators embedded in the cavity walls. These attempts achieved partial success, but ultimately failed to match experimental data across the full range of frequencies. The more they tried to patch the theory, the clearer it became that something fundamental was missing. The failure of classical physics to explain blackbody radiation was not just a technical issue. It struck at the philosophical heart of 19th-century science. Classical physics assumed continuity. Positions could vary smoothly, energies could take any value, and changes occurred gradually. The ultraviolet catastrophe suggested that this picture might break down at small scales. If energy truly flowed continuously, the catastrophe was unavoidable. Nature itself seemed to be rejecting one of the core assumptions of classical thought. What made the situation even more uncomfortable was that experimental evidence was undeniable. Improved instruments allowed scientists to measure radiation spectra with increasing precision. These measurements consistently confirmed the same curve, regardless of the material used to construct the blackbody cavity. The universality of the result meant that the problem could not be blamed on experimental error or material imperfections. The flaw lay squarely in theory. As the century drew to a close, blackbody radiation became a symbol of unresolved tension in physics. It was discussed at conferences, debated in journals, and quietly worried over by leading scientists. Some hoped that a clever mathematical reformulation would rescue classical ideas. Others suspected that a deeper conceptual shift was needed, but hesitated to say so openly. The success of classical physics had been so overwhelming that the idea of its failure felt almost unthinkable. This intellectual struggle revealed an important truth about scientific progress. Even the most successful theories have limits. Classical physics worked extraordinarily well for everyday phenomena and large-scale systems, but blackbody radiation exposed a boundary beyond which it could not pass. The equations did not merely need refinement, they needed replacement at a foundational level. Yet no one at the time knew what that replacement should look like. The crisis also highlighted the growing gap between mathematics and physical intuition. Mathematically, the divergence at high frequencies was clear and unavoidable within classical assumptions. Physically, infinite energy made no sense. This disconnect forced physicists to confront the possibility that their intuitive understanding of energy and radiation was incomplete. The universe was not obligated to conform to human expectations of smoothness and continuity. In hindsight, the failure of classical physics to explain blackbody radiation can be seen as a necessary step toward a deeper understanding of nature. At the time, however, it was a source of confusion and frustration. The problem resisted all conventional solutions and lingered like an unresolved mystery. It created the conditions in which a radical idea could eventually emerge, even if that idea initially appeared as nothing more than a mathematical trick. This failure also demonstrated the power of experimental evidence in guiding theory. No matter how elegant the equations or how respected the principles, they could not survive in the face of repeated contradiction by observation. Blackbody radiation served as a reminder that physics is ultimately accountable to nature, not to tradition. The experiments were speaking clearly, even if scientists were not yet ready to fully understand what they were saying. By exposing the limits of classical physics, blackbody radiation prepared the ground for a transformation in scientific thinking. It forced physicists to reconsider assumptions that had gone unquestioned for decades. While the solution had not yet appeared, the problem itself was already reshaping the intellectual landscape. The old framework was cracking, and through those cracks, a new view of reality would soon begin to emerge. As the failure of classical physics became impossible to ignore, the atmosphere within the scientific community slowly shifted from confidence to unease. Blackbody radiation was no longer seen as a minor anomaly, but as a warning sign that something essential was missing from the prevailing world view. Physicists were confronted with an uncomfortable realization. The mathematical tools that had explained so much of nature were now leading them toward physical absurdities. Infinite energy was not merely unrealistic. It was a declaration that the theory itself had reached a breaking point. What made this crisis especially profound was that it emerged from the most trusted pillars of physics. Thermodynamics, which governed heat and energy, had been refined through decades of careful experimentation. Electromagnetism, unified through Maxwell's equations, was one of the greatest triumphs of 19th century science. These frameworks were not speculative, they were proven. Yet when applied to radiation inside a cavity, they produced results that nature simply refused to follow. This contradiction forced physicists to confront a difficult question. Could the laws they trusted so deeply be fundamentally incomplete? Attempts to rescue classical physics grew increasingly creative. Some scientists tried to alter the physical assumptions behind radiation, suggesting that matter and electromagnetic waves exchanged energy in more complex ways than previously imagined. Others proposed that microscopic oscillators in the walls of a cavity might behave differently at high frequencies. These ideas were not unreasonable, and some matched experimental data over limited ranges, but none provided a universal explanation. Every partial success was followed by failure at another frequency or temperature. The pattern of frustration repeated itself again and again. The deeper issue was that classical physics treated energy as something endlessly divisible. No matter how small a portion one considered, energy could always be divided further. This assumption was woven so tightly into physical thinking that it was rarely questioned. Yet Blackbody radiation suggested that this very assumption might be the source of the problem. If energy could not be divided infinitely, then the runaway predictions at high frequencies might be avoided. Still, such an idea felt radical and almost heretical within the context of the time. As discussions intensified, a quiet philosophical tension emerged. Physics had long relied on continuity as a guiding principle. Smooth curves, continuous motion, and gradual change defined the classical image of nature. Discontinuity was associated with imperfections or approximations, not fundamental laws. To suggest that nature itself might operate in discrete steps was to challenge a deeply ingrained belief about how the universe should behave. For many physicists, this was not just a technical issue, but a challenge to their intuition about reality. Experimental evidence continued to apply pressure. As measurement techniques improved, the radiation curves became even more precise. The peak of emitted radiation shifted predictably with temperature, and the drop, off at high frequencies, was unmistakable. These results were reproducible across different laboratories and materials. The universality of the phenomenon stripped away any remaining hope that the problem lay in experimental error. Nature was delivering the same message again and again, and it was becoming increasingly difficult to ignore. This growing crisis revealed something important about the nature of scientific revolutions. They do not begin with dramatic declarations or sudden overthrows. Instead, they start quietly, through persistent failures that resist all conventional solutions. Blackbody radiation was such a failure. It did not overthrow classical physics overnight, but it weakened its foundations steadily and relentlessly. Each failed explanation made the old framework less convincing and prepared the scientific community, psychologically and intellectually, for a new way of thinking. At the same time, the crisis highlighted the limits of purely mathematical reasoning, when disconnected from physical meaning. Classical equations produced results that were internally consistent yet physically impossible. This gap forced physicists to reconsider the relationship between mathematics and reality. Equations were powerful tools, but they were not infallible guides to truth. When mathematics contradicted observation so dramatically, it was a signal that the underlying assumptions needed re-examination. The inability of classical physics to explain blackbody radiation also had broader implications beyond this single problem. It raised questions about other areas where classical theory might fail under extreme conditions. If continuity broke down at high frequencies, might it also fail at very small scales or very high energies? These questions lingered in the background, subtly expanding the scope of the crisis. Blackbody radiation was no longer an isolated puzzle. It was a gateway to deeper uncertainties. Within this atmosphere of tension and doubt, physicists found themselves at a crossroads. One path involved clinging to classical ideas and hoping that a clever adjustment would eventually resolve the issue. The other path required questioning assumptions that had long been considered untouchable. Choosing the second path demanded intellectual courage, because it meant accepting that centuries of accumulated understanding might need revision. For many, this was not an easy step to take. Yet it was precisely this environment of unresolved contradiction that made transformation possible. The failure of classical physics created a conceptual vacuum, a space where new ideas could emerge. Without the ultraviolet catastrophe, there would have been no urgency to rethink the nature of energy and radiation. The crisis did not provide answers, but it made the right questions unavoidable. It forced physicists to ask not just how radiation behaved, but what energy truly was at a fundamental level. Looking back, it becomes clear that blackbody radiation played a crucial role in reshaping modern physics. It exposed the limitations of a world that had seemed complete and unassailable. By doing so, it prepared the scientific community for a profound shift in understanding. The classical picture of a smooth, continuous universe was no longer sufficient. Something new was required, even if its shape and meaning were not yet clear. This moment of failure was, paradoxically, a moment of progress. Science advances not only through success, but through the recognition of its own limits. Blackbody radiation forced physics to confront those limits openly. It revealed that nature was more subtle and more complex than classical theories allowed. In doing so, it set the stage for ideas that would soon redefine reality itself. The inability of classical physics to explain blackbody radiation was not the end of an era, but the beginning of a deeper one. It marked the point where certainty gave way to questioning and confidence gave way to curiosity. The crisis did not destroy physics, it transformed it. From this failure emerged the conditions necessary for a new framework, one that would embrace discontinuity, probability, and limits to knowledge. Though the solution had not yet fully appeared, the path toward quantum physics had already been opened. Max Planck approached the problem of blackbody radiation with a mindset shaped by tradition, discipline, and deep respect for classical physics. He was not a revolutionary by temperament, nor did he see himself as someone destined to overturn the foundations of science. In fact, Planck was known among his peers as cautious, even conservative. He believed strongly in the established laws of physics, especially thermodynamics, which he regarded as universally valid. When the radiation problem resisted explanation, his instinct was not to challenge these laws, but to protect them. At the time, physics was built on continuity and determinism. Energy flowed smoothly, causes produced predictable effects, and nature followed precise mathematical rules that could, in principle, be fully understood. Planck was deeply committed to this world. He had built his career on the idea that physical laws were absolute truths rather than provisional models. This belief shaped how he approached every scientific problem, including Blackbody radiation. To him, the experimental results were not evidence that classical physics was wrong, but that physicists had not yet found the correct mathematical description. Planck's initial engagement with the radiation problem was motivated by his interest in thermodynamics rather than electromagnetism. He focused on entropy, a concept central to the second law of thermodynamics. He believed that if radiation could be described in terms of entropy, then its behavior could be brought under the firm control of thermodynamic principles. This approach reflected his broader philosophy. Physics should be grounded in universal laws, not ad hoc assumptions. His goal was to derive a radiation formula that fit experimental data while remaining faithful to classical reasoning. As experimental measurements became more precise, the pressure on theorists increased. Empirical formulas existed that matched parts of the radiation spectrum, but they lacked theoretical justification. Planck found this situation deeply unsatisfying. He wanted a formula that was not just accurate, but meaningful. For him, mathematics was not merely a tool for fitting curves. It was a window into the underlying order of nature. Any solution that lacked a solid theoretical foundation felt incomplete. Planck spent years working on this problem, exploring different mathematical routes. He studied how energy might be distributed among oscillators in the walls of a cavity, using models inspired by classical mechanics. Each attempt brought him closer to the experimental curve, but never close enough. The failures were frustrating, but they did not shake his faith in classical physics. Instead, they reinforced his belief that the right mathematical insight had simply not yet been found. What distinguished Planck from some of his contemporaries was his refusal to abandon thermodynamics as a guiding principle. While others were willing to explore speculative mechanical models, Planck insisted that entropy must play a central role. He believed that entropy was more fundamental than mechanics, and that it could reveal truths about radiation that mechanical models could not. This conviction guided his calculations and narrowed the range of solutions he was willing to consider. Eventually, Planck arrived at a mathematical expression that matched the experimental data perfectly. However, to derive it, he had to introduce a new assumption about how energy was exchanged between matter and radiation. Instead of allowing energy to vary continuously, he assumed it could only change in discrete amounts proportional to frequency. Importantly, Planck did not view this as a statement about physical reality. To him, it was a mathematical device, a formal step introduced to make the entropy calculation work. This distinction is crucial to understanding Planck's mindset. He did not believe that energy was actually quantized in nature. He saw quantization as a calculational trick, not a description of how the world truly functioned. His priority was to obtain the correct formula, not to interpret its deeper meaning. In his view, once the mathematics was fixed, a classical explanation might eventually be found that removed the need for such a strange assumption. Planck's reluctance to interpret his own result reflects his broader scientific philosophy. He believed that new physical concepts should emerge slowly and only when absolutely necessary. Radical interpretations, in his view, risked undermining the stability of science. By treating quantization as a temporary tool rather than a fundamental principle, he hoped to preserve continuity with classical physics. His solution was meant to repair the existing framework, not replace it. This cautious attitude also explains why Planck was initially surprised by the reaction to his work. While the mathematical success of his formula was immediately recognized, its conceptual implications were not fully appreciated at first. Planck himself presented the result with minimal emphasis on its novelty. He focused on the agreement with experiment and downplayed the unusual assumption behind it. In his mind, the problem had been solved in a technical sense, and the deeper interpretation could wait. The idea that Planck accidentally created quantum physics becomes clearer when one considers his intentions. He was not trying to redefine energy, matter, or reality. He was trying to solve a specific problem within the existing theoretical framework. The revolutionary consequences of his assumption were unintended. They emerged not from his goals, but from the internal logic of the mathematics he used. This situation highlights an important aspect of scientific discovery. Breakthroughs do not always come from bold visions or radical proposals. Sometimes they arise from conservative efforts to preserve established ideas. Planck's work is a perfect example of this dynamic. His loyalty to thermodynamics pushed him to introduce an assumption that classical physics could not ultimately absorb. In trying to save the old framework, he planted the seeds of a new one. Planck's own reaction to the later development of quantum theory further underscores his original intentions. When Einstein and others began to interpret energy quantization as physically real, Planck was hesitant. He admired Einstein's work, but he remained uneasy about abandoning continuity. Even as quantum ideas gained support, Planck hoped they would eventually be reconciled with classical physics. His caution persisted long after the scientific community began to move in a different direction. This tension between intention and outcome is central to the story of Planck's contribution. He did not set out to change physics forever. He set out to find the correct equation. Yet equations have consequences, and once introduced, they take on a life of their own. Planck's constant, originally just a proportionality factor in a formula, became a fundamental parameter of nature. It marked a boundary between the classical and quantum worlds, whether Planck liked it or not. The fact that such a profound shift emerged from such a modest intention is one of the most striking aspects of this episode in scientific history. It challenges the idea that revolutions are always driven by revolutionary thinkers. Planck was methodical, disciplined, and deeply respectful of tradition. Yet his work triggered a transformation more radical than anything he could have imagined. In hindsight, it is tempting to portray Planck as a visionary who foresaw the quantum revolution. This interpretation, however, does not do justice to the historical reality. Planck was a reluctant pioneer. His greatness lies not in his willingness to overthrow classical physics, but in his intellectual honesty. When faced with a problem that resisted all conventional solutions, he chose mathematical consistency over philosophical comfort, even if he did not fully accept the implications. This episode also reveals how science advances through a complex interplay of intention, method, and consequence. Planck's intention was conservative, his method was rigorous, and the consequence was revolutionary. None of these elements alone explains the outcome. It was their combination that produced one of the most important turning points in the history of physics. By searching for a mathematical fix rather than a conceptual revolution, Planck demonstrated the power of careful, disciplined work. He did not chase novelty for its own sake. He followed the logic of his equations wherever they led, even when that logic pointed beyond the boundaries of accepted thought. This willingness to follow mathematics while postponing interpretation allowed a new framework to emerge organically. In the end, Planck's approach reminds us that scientific revolutions are often recognized only in retrospect. At the moment of discovery, they may look like small adjustments or technical solutions. Planck believed he had solved a narrow problem in radiation theory. History revealed that he had opened the door to an entirely new understanding of nature. His search for a mathematical fix, grounded in respect for classical physics, became the accidental starting point of quantum physics. As Planck's formula began to circulate within the scientific community, its success was undeniable. It matched experimental data across the entire spectrum of blackbody radiation with a precision that no previous theory had achieved. Yet this success created a strange tension. The mathematics worked perfectly, but the assumption behind it remained deeply unsettling. Energy arriving in discrete portions contradicted everything classical physics stood for. Planck himself felt this discomfort strongly, and his reaction revealed just how unintended the broader consequences of his work truly were. Rather than celebrating a breakthrough, Planck treated his result with restraint. He presented it as a formal solution, carefully avoiding bold claims about the nature of energy. In his mind, the quantization assumption was a temporary measure, a placeholder until a more acceptable classical explanation could be found. This attitude shaped how his work was initially received. Many physicists admired the formula's accuracy, but shared Planck's reluctance to interpret it literally. The idea seemed too strange, too disruptive, to accept without hesitation. What followed was a period of quiet uncertainty. Planck's equation sat uneasily within the existing framework of physics. It worked, but it did not belong. Classical theory had no place for indivisible packets of energy, yet the experimental evidence left little room for doubt. This mismatch created a conceptual gap. Physicists could use the formula to calculate results, but they struggled to explain why it worked. The success of the mathematics was outpacing understanding, and this imbalance made many uneasy. During this time, Planck continued to hope that the quantization step could be removed or reinterpreted. He believed that a deeper classical mechanism might eventually emerge, one that would reproduce his formula without abandoning continuity. This hope was not unreasonable, given the history of physics. Many earlier crises had been resolved through refinements rather than revolutions. Planck saw no reason to assume that this case would be different. However, the situation began to change when other physicists approached the problem from new angles. Albert Einstein, in particular, took Planck's assumption seriously in a way Planck never intended. Instead of treating energy quanta as a mathematical convenience, Einstein argued that they represented a real physical feature of light itself. His explanation of the photoelectric effect relied directly on this interpretation, and it succeeded where classical wave theory had failed. This development shifted the conversation dramatically. For Planck, this was both validating and troubling. On one hand, it confirmed the power of the idea he had introduced. On the other, it pushed the interpretation far beyond what he was comfortable accepting. The notion that light could behave as discrete particles challenged the wave-based picture that had been so successful in explaining optical phenomena. Planck admired Einstein's insight, but he remained cautious. He saw these developments as provisional steps rather than final truths. As more evidence accumulated, the resistance to quantum ideas gradually weakened. Applications of quantization began to appear in atomic theory, specific heat, and spectroscopy. Each success reinforced the idea that discrete energy levels were not just a calculational trick, but a fundamental aspect of nature. Still, Planck's own attitude remained reserved. He accepted the practical usefulness of quantum concepts long before he fully embraced their philosophical implications. This gap between Planck's intentions and the direction physics was taking illustrates a crucial aspect of scientific change. Innovations often acquire meanings their creators never anticipated. Once an idea enters the scientific landscape, it becomes subject to reinterpretation, extension, and transformation by others. Planck's role was not to build the entire quantum framework, but to introduce a key element that made it possible. The revolution unfolded around him rather than being driven by him. The gradual acceptance of quantum ideas also reveals how scientific communities adapt to radical change. New concepts rarely gain immediate acceptance, especially when they conflict with established intuition. Instead, they are tested, debated, and often resisted. Planck's cautious presentation of his work allowed his formula to be evaluated on empirical grounds without forcing an immediate philosophical commitment. This may have helped the idea survive its early years of uncertainty. Over time, the cumulative weight of evidence made it increasingly difficult to maintain a purely classical interpretation. Each successful application of quantization chipped away at the old assumptions. What began as a mathematical fix slowly transformed into a new way of thinking about energy and matter. The transition was not sudden, but gradual, marked by periods of doubt and reassessment. Planck himself witnessed this shift, even if he never fully embraced its most radical implications. This evolution underscores the accidental nature of Planck's contribution. He did not propose a new world, view, or seek to redefine reality. He responded to a specific technical problem using the tools and beliefs he trusted most. The revolutionary impact of his solution emerged only when others pushed the idea beyond its original context. In this sense, quantum physics was not invented in a single moment, but grew out of a series of reinterpretations and extensions. Planck's story challenges common narratives about scientific genius. It shows that transformative ideas can arise from caution as much as from boldness. Planck's strength lay in his rigor and honesty. He refused to ignore experimental facts, even when they forced him to introduce an assumption he found uncomfortable. This commitment to consistency allowed a new framework to emerge, even if he himself did not fully welcome it. The unintended consequences of Planck's work also highlight the importance of intellectual openness in science. While Planck remained cautious, the scientific community as a whole was willing to explore the implications of his idea. This collective process of exploration and debate turned a narrow solution into a foundational principle. The quantum revolution was not the product of a single mind, but of a shared willingness to follow evidence wherever it led. In retrospect, Planck's search for a mathematical fix appears as a pivotal moment in the history of physics. It represents the point at which classical certainty gave way to quantum possibility. The fact that this shift emerged from conservative intentions rather than radical ambition makes it all the more striking. It reminds us that the path of discovery is rarely straightforward, and that the greatest changes often begin quietly, almost unnoticed. By the time quantum theory became firmly established, Planck's role was secure, even if his feelings remained mixed. His name became permanently associated with the constant that defines the quantum scale. What began as a desperate mathematical step evolved into a cornerstone of modern physics. Planck may not have sought a revolution, but his careful search for a solution made one inevitable. As Max Planck struggled to reconcile theory with experiment, he found himself cornered by a problem that refused to yield to any classical solution. Years of careful work had led him to a dead end. Every established method failed, yet the experimental evidence was unambiguous and relentless. The radiation curves were precise, repeatable, and universal. Ignoring them was not an option. For a physicist who valued logical consistency and empirical truth above all else, this situation created an intellectual crisis. Something had to give. Planck's calculations showed that if energy were treated as a continuous quantity, the mathematics inevitably led to the ultraviolet catastrophe. No amount of refinement could remove the divergence at high frequencies. The equations were unforgiving. At this point, Planck faced a choice. He could reject the experiments, which he trusted deeply, or he could question one of the most basic assumptions of classical physics. Reluctantly, and with no enthusiasm for the consequences, he chose the latter. The assumption he introduced was simple in form but radical in implication. Instead of allowing energy to vary smoothly, he proposed that energy could only be exchanged in discrete amounts. These amounts were proportional to the frequency of radiation, multiplied by a new constant. Planck did not arrive at this idea through philosophical speculation or a desire to reshape physics. It emerged as a last resort, a mathematical maneuver designed to make the entropy calculations work and to bring theory into agreement with observation. What is crucial to understand is that Planck himself did not believe this assumption described physical reality. He viewed it as a formal device, a convenient fiction that allowed him to derive the correct formula. In his mind, the quantization of energy was not a statement about nature, but a temporary step introduced under pressure. He fully expected that a deeper classical explanation would eventually eliminate the need for such an artificial restriction. This reluctant attitude reveals why energy quantization can rightly be described as a desperate assumption. It was not embraced with excitement or confidence. It was adopted with hesitation, almost regret. Planck was well aware that discreteness clashed with the continuous world, that had dominated physics for centuries. Accepting it as fundamental would have meant abandoning deeply held beliefs about how nature operates. He was not ready to take that step. Despite his reservations, the assumption worked flawlessly. Once energy exchanges were restricted to discrete units, the calculations fell into place. The predicted radiation spectrum matched experimental results across all frequencies and temperatures. The mathematical success was immediate and undeniable. For Planck, this was both a relief and a source of discomfort. He had solved the problem, but at the cost of introducing an idea he did not trust. At first, the scientific community shared his caution. Many physicists treated the quantization step as a clever trick rather than a physical principle. The focus remained on the accuracy of the formula, not on the meaning of its assumptions. This cautious reception allowed the idea to exist without immediately challenging the foundations of classical physics. Energy quantization was tolerated, not celebrated. However, assumptions have consequences. Once introduced, they influence how problems are approached and understood. Planck's discrete energy elements, though initially intended as a mathematical convenience, opened a door that could not easily be closed. They suggested that nature might operate differently at small scales, that continuity might be an approximation rather than an absolute truth. Even if Planck resisted this interpretation, the idea itself carried revolutionary potential. The desperation behind the assumption makes its impact even more remarkable. It was not the product of bold imagination, but of intellectual honesty. Planck refused to ignore experimental facts. even when they forced him into uncomfortable territory. He chose consistency with observation over loyalty to tradition. In doing so, he demonstrated a core principle of science: when reality and theory conflict, theory must bend. Energy quantization did not immediately overturn physics, but it planted a seed: the negative charge of electrons and the positive charge of nuclei dictate bond lengths. What began as a reluctant compromise became the foundation of a new framework. The assumption that energy comes in discrete units would eventually redefine atoms, light, and matter itself. In hindsight, the desperation of Planck's assumption is precisely what makes it so powerful. It shows that transformative ideas do not always arise from confidence or vision. Sometimes they emerge from necessity, from the refusal to accept failure. Planck did not seek to change the world of physics, but his willingness to make a single uncomfortable assumption changed it forever. When Max Planck introduced his new constant into physics, he could not have imagined how deeply it would reshape humanity's understanding of nature. At first, it appeared to be nothing more than a numerical factor, a small quantity inserted into an equation to make theory match experiment. Yet this constant quietly carried a revolutionary message. It marked a fundamental limit, a boundary beyond which classical ideas about measurement, energy, and continuity could no longer be trusted. The constant linked energy to frequency, establishing a proportional relationship that had never existed before. This connection suggested that energy exchange was not arbitrary but structured. Nature, it implied, had a built-in scale. Unlike classical physics, which allowed quantities to be divided endlessly, the presence of this constant introduced a smallest meaningful action. Below this scale, the familiar rules began to blur. Even though Planck himself did not initially embrace this interpretation, the constant made it unavoidable. One of the most profound effects of this constant was how it changed the way physicists thought about measurement. In classical physics, measurement was assumed to be passive. One could, in principle, observe a system without disturbing it. Planck's constant undermined this assumption. It suggested that any attempt to measure energy, position, or motion at very small scales would involve discrete interactions. Observation itself became an active process, inseparable from the phenomena being observed. As physicists began to work with the constant, they discovered that it set the scale at which quantum effects became important. When physical systems involved energies or dimensions much larger than this scale, classical physics remained an excellent approximation. But as systems approached this limit, classical predictions failed. The constant acted like a dividing line between two regimes of nature. On one side lay the familiar world of everyday experience. On the other lay a domain where intuition no longer applied. This shift had deep philosophical implications. The constant implied that uncertainty was not merely a result of imperfect instruments or incomplete knowledge. Instead, it was woven into the fabric of reality itself. Physical quantities could not be specified with unlimited precision because nature did not allow it. The idea that the universe imposed fundamental limits on what could be known challenged centuries of scientific optimism. Knowledge itself had boundaries. The constant also transformed how physicists understood stability in nature. Classical models of atoms predicted that electrons should radiate energy continuously and spiral into the nucleus, making atoms inherently unstable. The introduction of a fundamental quantum scale changed this picture. Energy levels became discrete, and transitions between them involved specific amounts of energy. Stability was no longer mysterious. It emerged naturally from quantization. Matter could exist in persistent, well-defined states. Beyond atomic physics, the constant influenced how energy and time were related. It suggested that processes occurring over very short timescales involved correspondingly large uncertainties in energy. This insight reshaped the study of transient phenomena and decay processes. Events were no longer described solely by smooth trajectories, but by probabilities constrained by fundamental limits. Time itself took on a new role, intertwined with energy in ways classical physics had never anticipated. Perhaps most importantly, the constant redefined what it meant for a theory to be fundamental. Classical physics had aimed for complete determinism, the idea that the future could be predicted exactly from the present. The presence of a fundamental constant that enforced limits on precision made this goal unattainable at the deepest level. Physics could still make powerful predictions, but these predictions were statistical rather than absolute. Probability replaced certainty as a core concept. The quiet power of Planck's constant lies in its universality. It appears in every corner of quantum theory, from the behavior of light and electrons to the structure of solids and the dynamics of the early universe. It does not depend on the material, the environment, or the observer. It is a property of nature itself. This universality elevates it from a mere parameter to a defining feature of reality. What makes this transformation especially striking is that it began with no intention of changing how nature is measured or understood. Planck introduced the constant reluctantly as part of a mathematical solution. Yet once in place, it reshaped the conceptual foundations of physics. It forced scientists to rethink measurement, knowledge, stability, and determinism. A single number became a gateway to a new worldview. In the end, Planck's constant stands as a reminder that small ideas can carry immense consequences. It quietly signaled the end of the classical dream of unlimited precision and complete predictability. By setting a fundamental scale for nature, it changed not only how physicists calculate, but how they think about reality itself. When the idea of a fundamental constant entered physics through Planck's work, it quietly altered the meaning of measurement in a way that no previous discovery had done. Before this moment, measurement was seen as a matter of refinement. If instruments were improved enough, nature would eventually reveal its exact values. Any uncertainty was assumed to be temporary, a limitation of human technology rather than a feature of reality itself. Planck's constant challenged this belief at its core by introducing a natural scale that could not be bypassed, no matter how advanced measurement tools became. This constant did more than connect energy and frequency. It defined the smallest meaningful unit of physical action. Below this scale, classical concepts such as precise position, exact momentum, or continuous energy lost their clear meaning. Measurement was no longer simply about reading values from nature. It became an interaction governed by unavoidable limits. To measure something at very small scales required exchanges of energy that could not be made arbitrarily small, and those exchanges altered the system being measured. As physicists began to work with this constant, they realized that it imposed a fundamental granularity on observation. Measuring an object was no longer a passive act. Any attempt to observe microscopic behavior required discrete interactions, each constrained by this constant. The observer could not be separated from the observed. Measurement itself became part of the physical process, blurring the line between what is being measured and how it is measured. This shift forced a re-evaluation of precision. In classical physics, precision was limited only by practical considerations. In the new framework shaped by Planck's constant, precision encountered an absolute boundary. Certain pairs of physical quantities could not both be known exactly, not because of experimental flaws, but because nature did not allow it. Measurement outcomes became inherently probabilistic, even under ideal conditions. This was a profound departure from the belief that the universe was fully deterministic at all scales. The presence of a fundamental measurement scale also explained why classical physics worked so well in everyday life. For large objects and low frequencies, the effects governed by this constant were vanishingly small. The discrete structure of energy and action was effectively hidden, making the world appear smooth and continuous. Classical measurement emerged as an approximation, valid only when the quantum scale could be ignored. This realization reframed classical physics not as wrong, but as incomplete. Planck's constant also changed how time was understood in measurement. Very short intervals of time were linked to uncertainties in energy, suggesting that rapid processes could not be tracked with arbitrary accuracy. Events at extremely small timescales resisted classical description. Measurement became a balance between time resolution and energy disturbance, revealing that time itself was subject to fundamental constraints. This insight reshaped how physicists thought about decay, transitions, and fleeting phenomena. The constant's influence extended beyond laboratories and equations. It altered the philosophical meaning of knowledge in science. If nature itself imposed limits on what could be measured, then complete knowledge of a system was not just difficult, but impossible. This realization marked a departure from the classical ideal of total predictability. Physics shifted from seeking exact trajectories and outcomes to predicting probabilities and distributions. Measurement became a statistical enterprise rooted in fundamental law. What makes this transformation remarkable is how quietly it occurred. Planck did not announce a new theory of measurement. He introduced a number, small and seemingly technical. Yet that number carried with it a radical message. Reality has a built-in scale that defines what can and cannot be observed. Measurement was no longer a neutral window into nature, but a process shaped by nature's own limits. As quantum theory developed, Planck's constant appeared everywhere, reinforcing its role as a universal boundary. It governed atomic structure, controlled radiation, and defined the behavior of particles and waves alike. Wherever it appeared, it carried the same implication. Measurement could never escape its influence. The constant unified diverse phenomena under a single principle, tying together energy, time, and observation. In retrospect, this change in measurement may be one of the most significant consequences of Planck's work. Technologies, theories, and experiments all depend on how measurement is understood. By redefining its limits, Planck's constant reshaped the entire scientific method at small scales. It taught physicists that nature does not simply reveal itself more clearly as instruments improve. Instead, nature responds according to rules that set permanent boundaries. The transformation of measurement was not something Planck intended, but it became one of his most enduring legacies. A single constant quietly redefined precision, certainty, and knowledge itself. Through it, physics learned that understanding the universe means accepting not only what can be measured, but also what must forever remain uncertain. When Max Planck introduced the idea that energy might be exchanged in discrete units, he did so with deep reluctance. From the very beginning, he struggled with the meaning of his own assumption. To him, it felt unnatural and even disturbing. Planck had spent his career defending the principles of classical physics, especially continuity and determinism. The suggestion that energy came in indivisible portions conflicted with everything he believed about how nature should behave. As a result, he never fully trusted the physical reality of the concept he had introduced. Planck's doubts were not superficial. They were rooted in his philosophical view of science. He believed that physical laws existed independently of human interpretation, and that these laws were smooth, orderly, and absolute. Quantization, by contrast, appeared artificial. It seemed like a mathematical rule imposed from the outside rather than a natural principle arising from deeper laws. For this reason, Planck regarded energy quanta as a temporary feature of his calculations, not a permanent feature of nature. Even after his radiation formula achieved widespread recognition, Planck remained cautious. He emphasized that his result did not necessarily imply a fundamental break with classical physics. In his own writings, he repeatedly expressed hope that the quantization assumption would eventually be replaced by a more acceptable explanation grounded in classical theory. To him, the true task of physics was to uncover universal laws, not to introduce exceptions that disrupted continuity. This internal conflict shaped Planck's reaction to later developments in quantum theory. When Albert Einstein proposed that light itself consisted of discrete packets of energy, Planck admired the brilliance of the idea, but hesitated to accept its implications. The notion that electromagnetic radiation could behave like particles challenged the wave theory that had been so successful. Planck supported Einstein professionally, even helping him secure academic positions, but he remained uneasy about the physical interpretation of light quanta. Planck's skepticism highlights an important truth about scientific discovery. Being the originator of an idea does not guarantee comfort with its consequences. Planck was willing to accept quantization as a calculational tool, but not as a description of reality. He drew a clear line between mathematical success and physical meaning. This distinction allowed him to preserve his philosophical commitments, even as physics around him began to change. As quantum ideas gained empirical support, Planck's position became increasingly difficult to maintain. Experiments on the photoelectric effect, atomic spectra, and specific heat all pointed toward the reality of discrete energy levels. These results suggested that quantization was not merely a convenient assumption, but a fundamental property of nature. Still, Planck approached these developments with restraint. He accepted the results without fully embracing the underlying world view. This hesitation reveals how deeply classical intuition was embedded in early 20th century physics. Continuity had been a guiding principle for centuries, shaping not only equations but also expectations about reality. To abandon it required more than evidence. It required a shift in mindset. Planck, shaped by an earlier generation, found this shift difficult. His doubts were not a sign of weakness, but a reflection of intellectual honesty and loyalty to established principles. Planck's struggle also illustrates the human side of scientific revolutions. Scientific change is often portrayed as a smooth progression driven by logic alone. In reality, it involves tension, uncertainty, and emotional resistance. Planck had to live with the knowledge that his own work had introduced an idea he could not fully accept. This personal conflict makes his story more compelling and more authentic. Over time, the quantum framework grew stronger and more coherent. New theories incorporated quantization as a central principle rather than an awkward exception. Younger physicists, less attached to classical continuity, embraced the new ideas more readily. As this happened, Planck's role shifted from reluctant innovator to respected founder. Even if he never fully adopted the quantum world, his contribution became undeniable. Planck's doubts did not diminish the importance of his work. On the contrary, they emphasize its significance. By introducing an idea he personally questioned, Planck demonstrated a commitment to scientific integrity. He did not reject a result simply because it conflicted with his beliefs. He allowed evidence and mathematics to guide him, even when they led to uncomfortable conclusions. In the end, Planck's skepticism reminds us that revolutions in science are rarely embraced unanimously, even by their originators. New ideas often feel wrong before they feel right. Planck's reluctance underscores the depth of the shift quantum theory represented. It was not just a new set of equations, but a challenge to centuries of intuition. That Planck could open the door to such a change, despite his doubts, stands as one of the most remarkable achievements in the history of physics. As Planck's idea of quantized energy began to circulate, its impact extended far beyond the narrow problem of Blackbody radiation. What had started as a mathematical device soon revealed its potential to explain phenomena that classical physics could not touch. Einstein's work on the photoelectric effect was one of the first clear examples. By taking Planck's assumptions seriously, Einstein showed that light itself could behave as discrete packets of energy, later called photons. This interpretation transformed Planck's mathematical trick into a principle with real physical meaning, opening the door to a new understanding of light and matter. Before Einstein, light was universally treated as a continuous wave. Waves could interfere, diffract, and spread smoothly across space. Planck's constant implied that, at a fundamental level, energy could not vary continuously, but came in fixed increments. For phenomena such as the photoelectric effect, this insight explained why electrons were ejected only when light reached a certain frequency. Classical wave theory, which predicted gradual energy accumulation, could not account for this threshold behavior. Planck's formula, once reluctantly adopted, provided the key to a growing number of experimental puzzles. The transformation of Planck's formula into a physical principle illustrates how scientific ideas evolve beyond their originators' intentions. Planck himself was hesitant to claim that energy quanta reflected reality. He had introduced the concept to save a calculation, not to rewrite physics. Yet the logic of his equations forced a reinterpretation. Once other physicists applied the formula to broader contexts, it became clear that quantization was not just a mathematical convenience. It described a fundamental property of nature. The accidental assumption had become the cornerstone of a new scientific framework. As the quantum framework developed, it began to illuminate other long-standing problems. Classical physics had struggled to explain atomic stability. Electrons in orbit, according to classical electromagnetism, should radiate energy continuously and spiral into the nucleus. But if energy levels were discrete, as implied by Planck's assumption, electrons could only occupy certain stable orbits. Niels Bohr applied this reasoning in his atomic model, showing that quantized energy levels could explain spectral lines and the stability of atoms. Planck's constant, initially a parameter in a formula, became a universal marker of the quantum scale. The influence of Planck's constant also extended into thermodynamics and statistical mechanics. Specific heats of solids, previously unexplained by classical theory, could be accurately modeled when energy quantization was considered. Transitions between energy levels in molecules and atoms revealed patterns consistent with discrete energy exchange. Each of these applications reinforced the notion that quantization was not an anomaly but a fundamental principle. What had been a desperate mathematical fix now governed the behavior of matter at microscopic scales. Perhaps most strikingly, the extension of Planck's idea demonstrated how scientific revolutions can begin unintentionally. Planck did not seek to create a new physics. He sought only to reconcile theory with experiment. Yet the logic of his work, combined with subsequent reinterpretations, reshaped the entire field. Quantum theory grew organically from the seeds he had planted, even though he himself did not fully anticipate its consequences. This process highlights the unpredictable and collaborative nature of scientific discovery. The broader scientific community gradually embraced these ideas, and Planck's constant became a unifying element. It appeared wherever quantum phenomena were observed, linking light, matter, and atomic structure under a single framework. The universality of the constant meant that it was not tied to any specific experiment or material, but reflected a property of the universe itself. Planck's reluctant invention thus became the measuring stick for a new layer of physical reality, defining the scale at which classical intuitions no longer applied. In the end, Planck's accidental creation of quantum physics illustrates a profound truth about scientific progress. The significance of an idea often extends far beyond the intentions of its originator. What began as a pragmatic assumption to solve a narrow problem grew into a principle that redefined reality. Planck's formula and the constant within it became foundational to the work of Einstein, Bohr, Heisenberg, and countless others. It reshaped our understanding of energy, matter, and the very limits of knowledge, proving that some of the most revolutionary ideas in science emerge not from bold ambition, but from the persistent pursuit of understanding. The birth of quantum physics is remarkable not only for its profound impact on science, but also for the accidental nature of its origin. Max Planck did not set out to overthrow centuries of classical physics. He merely sought to solve a stubborn problem in radiation theory. Yet his work, introduced cautiously and reluctantly, became the foundation of a revolution that transformed the way humans understand the universe. This highlights a key aspect of scientific progress. Profound discoveries often arise from unexpected circumstances, sometimes without the direct intention of the discoverer. Planck's approach to Blackbody radiation was methodical and conservative. He relied on well-established thermodynamic principles and believed firmly in the continuity of energy. When classical equations failed to match experimental observations, Planck was forced to introduce a radical assumption. Energy could only be exchanged in discrete amounts. To him, this quantization was a mathematical trick, a convenient way to make the calculations work. He did not claim that nature itself obeyed this rule. In other words, the most fundamental aspect of quantum theory, the idea of energy quanta, was born not from visionary insight, but from a desperate attempt to reconcile theory with experiment. The accidental nature of this discovery is emphasized by Planck's own attitude toward his work. Unlike Einstein, Bohr, or Heisenberg, Planck did not immediately recognize the far-reaching implications of energy quantization. He remained cautious and skeptical, hoping that a classical explanation would eventually emerge to replace the unusual assumption he had introduced. Yet, despite his hesitancy, the assumption contained the seeds of a new understanding. By creating a mathematical structure that accurately described Blackbody radiation, he unintentionally laid the groundwork for the entire field of quantum mechanics. Planck's reluctant innovation demonstrates that the origins of revolutionary ideas often lie in the convergence of necessity and ingenuity. The problem of Blackbody radiation forced him to act, and the constraints of mathematics guided his choices. While his goal was narrow, resolving a technical inconsistency, he inadvertently created a conceptual framework that would challenge centuries of physical intuition. This shows that scientific breakthroughs are not always the result of grand visions. Sometimes they emerge from careful attention to stubborn problems and the courage to follow the evidence where it leads. The subsequent development of quantum theory further underscores the accidental character of Planck's contribution. Einstein extended Planck's idea to explain the photoelectric effect. Niels Bohr applied it to atomic structure, and later physicists expanded it into a complete theoretical framework. Planck's constant, initially a proportionality factor, became a universal parameter defining the scale at which classical ideas fail. None of this was explicitly intended by Planck, yet all of it originated from his single step, the introduction of energy quanta to save his calculations. In hindsight, what appears inevitable was, at the moment, entirely unplanned. This accidental emergence also highlights the collaborative and cumulative nature of science. Planck provided the initial insight, but it required the work of others to fully realize its consequences. Einstein, Bohr, Heisenberg, Schrödinger, and others interpreted, extended, and applied his idea to a broad range of phenomena. The revolution was not the work of one person, yet it could not have occurred without Planck's initial step. His contribution serves as a reminder that breakthroughs often begin with small, deliberate actions that, unintentionally, open the door to larger transformations. Moreover, the accidental creation of quantum physics challenges conventional notions of genius. Planck was not a revolutionary by temperament, and he did not seek fame or recognition. His greatness lay in his intellectual honesty, precision, and willingness to follow evidence, even when it led him into uncomfortable territory. By solving a specific problem with rigor and care, he inadvertently initiated a paradigm shift that would forever alter our understanding of the universe. In this sense, the most transformative discoveries can arise from humility, discipline, and persistence, rather than bold ambition alone. Ultimately, Planck's accidental creation of quantum physics illustrates the unpredictable nature of scientific discovery. Sometimes the most profound changes emerge from practical problem solving rather than visionary foresight. A single idea, introduced cautiously to address a narrow issue, can ripple outward to transform entire fields of knowledge. Planck did not intend to revolutionize physics, yet his work reshaped reality itself. This serves as a powerful lesson. In science, as in life, even small, careful steps taken with integrity can lead to outcomes far beyond what was imagined.